So, in our course on selected topics, decision modeling, today we are in the 33rd lecture, that is on genetic algorithm process. Right. In our previous lecture, we have seen what is genetic algorithm, and we have understood that this is the first of the nature inspired algorithm, and the way the species, I mean as per the theory of Darwin, moves from generations to generations, and as they move from generations to generations, they improve upon the fitness to the environment, and through a process of say crossover, and sometimes also through a process of mutation. The similar thing is also adopted in case of optimization problems, and we create the population of feasible solutions, and there is a fitness function which is equivalent to the objective function, and if we have some solutions which are more fit than others, then they have more chance of getting selected, and out of them we have a crossover and a mutation process through which we create the new population for the next generation. And by this method, as we move from generations to generations, we create finally a set of feasible solutions with higher average fitness values, and the best one should be closer to the optimal solution. So, that is the method which we are calling as genetic algorithm. Now, there are many variations to the genetic algorithm process, and all these variations are essentially more of design concern, which depends on the problem at hand and to some extent to the designer as well. Right. So, having understood that, let us do a little recap, and then through an example try to understand what is really happening, I mean how to really carry out the genetic algorithm process, and then in the next lecture we shall see some examples. So, this is the basic process. As you can see that we start with a population. So, we initiate a population. This population is initiated through a random process, right, and as you initiate and then also evaluate the fitness of that population, and after that we first activity we do selection of parents based on the fitness function. So, obviously, those parents, I mean those feasible solutions which are having higher fitness value has more chance of getting selected. Then the parents who are selected, they go through a process of modification, sometimes called recombination, of crossover and mutation. Then after the crossover and mutation, the modification that occurs, then we have the modified offsprings, and these modified offsprings are then evaluated on the basis of what you call the fitness function again, and maybe sometimes some members are deleted and some members are directly added from the parent population, which is called elitism, and then that evaluated offspring that formulates the next generation population, and the process goes on till we find the average fitness value is improving, is all right. So, that is the evolutionary cycle of genetic algorithm through which the process continues. The very first process out of these is a measure of, that is encoding, is all right. So, an encoding process, that is the very first process. So, when we do encoding, the encoding requires there are different methods of encoding. One of the encoding is called the binary encoding. So, binary encoding is used sometimes. So, suppose I have a number let us say 4, then 4 can be written in binary as equal to 2 to the power 2 to the power 2 is all right. So, which is like 1 0 0. So, this 1 0 0 is 1 into 2 to the power 2, 0 into 2 to the power 1 and 0 into 2 to the power 0. So, that is how a binary numbers are written. So, you can represent some numbers through a chromosome, and that is called the binary encoding having zeros and ones. So, essentially like every chromosome should represent a feasible solution, right. So, here a population of 2 chromosomes are shown. Every chromosome is basically a feasible solution, is a feasible solution to the problem. Sometimes that we shall see later, it may not be a feasible solution, particularly where constraints are available. There is not just an objective function, but we also have what you call a number of constraints. Then how to handle them? Sometimes we also may keep some infeasible solutions and see to it that their fitness values are pretty low. Now, each bit corresponds to a gene. So, basically a chromosome is consisting of genes. So, here like this is a gene, this is another gene, this is another, like these there are so many of them, and the individual value for a gene is called an allele. So, there are alleles which are individual values of the genes, and the bits are essentially like a gene which can have a 0 or 1 in case of binary encoding. In case of real encoding, it could be numbers between 0 to 9 and A, B, C, D, E, F, G, etc., or you can also have sometimes hexadecimal or octal numbers, right. So, that is about the encoding, that is the first step. So, what we have to do, if you really go back to our previous slide, then you can see that the initiate the population. The population is to be initiated by defining a chromosome for a given solution. So, number of solutions, suppose you decide the length of population, number of chromosomes in a population, say 20. So, if you generate through a random means, maybe by using random numbers 20 chromosomes, then we have got a population to begin with. Is it all right? So, that is how we start or initiate. So, as we have initiated, then as I said, the next is the encoding, and I have shown you one kind of encoding, that is called the binary encoding. Now, binary encoding is difficult to apply directly and not a very natural encoding, but sometimes, as we shall see later in an example of where we have the knapsack problems, the binary encoding could be a good option. For some other problems, we may actually have value or real number encoding, sometimes for constraint optimization problems. So, here look here that each gene is actually a real number. Is it all right? Then for traveling salesman and similar such combinatorial optimization problems like quadratic assignment problems, like quadratic assignment problem comes like in facility location problems, where it is an assignment problem, but with a quadratic objective function. So, the method is go for what is known as a permutation encoding. So, you see this permutation encoding, this is an example. So, 35124876 could be a gene. So, you see this, suppose think of a traveling salesman problem. Let us hope say there are 8 cities. So, there are 8 cities, and a person has to go through all the cities exactly once before coming back to the city of origin. So, one such tour could be this 35124876. No city should occur more than once. So, that is called permutation encoding. So, another gene another chromosome could be something like 1, 2, 3, 4, 5, 6, 7, 8. Right. So, just going to the next city and after 8 coming back to 1, but that we need not encode. We can only encode this much to understand the particular the way the person moves from a city to the city. So, 8 to 1 will be considered in this particular case when we calculate the fitness function, taking those distances. An example I will show in the next lecture. So, that is how, and then obviously there is also another kind of encoding which is known as the tree encoding. This is very interesting kind of encoding. The tree encoding essentially is used when we are basically trying to find a formula. We want to discover a formula or a pattern, then we can have tree encoding, right. So, all these are different types of encoding. Obviously, they are to be applicable for different kind of problems, and a given problem should be having a type of encoding, right. So, once we know what is then encoding, we should also understand another very important thing, that we have a coding space and we have a solution space. The coding space and the solution space, they are two different things. See, the solution space is basically they are the actual solutions. So, assuming the same traveling salesman problem, the TS problem we are talking about, in the solution space we have a given tour, a particular tour that the salesman has to move from a city to another city to these, that is a particular tour, and that is in your solution space. On the other hand, the chromosome that you define for your or a number of such chromosome that you define for carrying out the problem, that is your coding space. So, the coding space and the solution space, as you can see, there could be feasible, this is the feasible solution space, there could be other solutions which are infeasible. So, there could be in the coding space we can have feasible solutions, we can have infeasible solutions for constraint problems, and there could be some that could be illegal ones, right. So, we should be careful that we should not we should define coding space in, first of all, if we can define in such a manner, so that only feasible solutions are available and nothing else. Say for example, suppose for a the traveling salesman problem, let us take a very simple 4 city problem. So, 1 4 2 3 is a feasible solution, all right. But what about this? Let us say 1 4 2 2, 1 4 2 2, what about 1 4 2 2? See, 1 4 2 2 is an infeasible, not only infeasible, you can even call it illegal in a sense that you just cannot really think of permutation going from city 1 to city 4, then city 2 and then city 2 again, is all right. So, it is not really possible. So, that is what. So, if you say that I will have only one number, I mean no number should be repeated in the chromosome, that is called permutation encoding, it automatically ensures a feasible solution will be created. Is all right. So, that means while you do encoding, see to it that try to see that all the chromosomes come from the feasible space. Is it all right? And if absolutely not possible, then accommodate some infeasible ones and take care of them by giving them low fitness values. Then there is mapping. You see, you should always try to see that there is a one-to-one mapping between the solution space and coding space. That means, every solution should be coded uniquely, differently. So, it should not be that one chromosome represents more than one solution, should not be, or similarly one solution should not be coded differently, one solution. So, there should be an 1:1 mapping. So, these are some of the things that should be remembered while going for encoding. So, these are the issues. The feasibility is an issue. Solution decoded from a chromosome lies in a feasible region of the problem. Then legality, chromosome represents a solution to the problem, it should not be something else. And uniqueness of mapping, that means there should be one-to-one mapping is highly desirable, right. So, there should be 1:1 mapping, and if possible absolutely if nothing can be done, then we should accommodate some infeasible solutions also with low fitness, but otherwise try to see the feasibility is maintained. That is what is required for encoding of chromosomes. In case of mapping the solution to the your coding set. Now comes the initialization. The initialization means that we have to first create the population for the first generation, population, we have to begin with somewhere. So, this is done through a process of randomization, right, a process of randomization through a local search procedure and selecting only feasible solutions, right, selecting feasible solutions. So, supposing consider a problem, minimize a function of x1, x2, x3, is it all right, and it is known that x1, x2, x3 they are in a range which is between 0 to 15. So, they are all hexadecimal numbers, that means supposing it is known that x1 varies from 0 to 15, x2 varies from 0 to 15 and x3 also varies from 0 to 15, is it all right. So, if this is so, what we can do, not only 15, maybe we are using something like this, yeah. So, 0 to 15. So, supposing if we use 4 bits to represent 1. So, you see the highest number is 1111 and the lowest number is 0000. So, these are all binary numbers. So, this is 2 to the power 3, 2 to the power 2, 2 to the power 1 and 2 to the power 0. So, you see this will be 8 plus 4 plus 2 plus 1. So, this is actually 15 and this is equal to 0. So, you see the any number in between will be between 0 and 15. So, through binary encoding, suppose we have a 12 digit string. So, this is our 12 digit string and we can represent a particular chromosome in this way, that first 4 bits will be x1, next 4 bits will be x2 and next 4 bits will be x3. So, supposing just arbitrarily assume, suppose the population size is say 8, supposing. So, we have to then have something like tossing 12 into 8 96 times, supposing we carry out tossing of a coin, is all right. So, that means let us toss 96 times a coin. So, a coin is tossed 96 times. Now, supposing head is 1 and tail is 0. So, supposing first we get a head, so I put 1, then a tail, so 0, head, head, 1, 1, then tail, tail, head, head, then head, tail, tail, head. So, that will be our first chromosome, is all right. So, that is the randomization that we are talking about. So, like these, if we do 12 times, I get 1 chromosome, and since the initial population size is let us say 8. So, if I do 96 times, I can create an initial population of the solutions, right. So, very simple process, a population is created. So, once the population is created, then we go to the next stage, that is, so here you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, here 10 chromosomes are created. So, 10 solutions are created. So, we had tossed something like 120 times. So, then assume the functional values I have not given, but just assume these are the fitness values, right. So, you see once again please recall that the first 4 were x 1, next 4 were x 2, next 4 were x 3. So, second one was not correct. So, this was first 4, then this is second 4, this is third 4. So, this was x 1, this was x 2, this was x 3. So, these are the 3 variables. Now, obviously, the objective function was a function of x 1, x 2, x 3. Supposing when I put this value of x 1, that means what is that value? 2 to the power 3, 8 plus 2, 10. Here 4 plus 1, 5, and here 8 plus 2, 10 once again. So, when you put those values, we get 13.2783. So, that we call as the fitness function value. So, you can see that the various chromosomes has got various fitness values. So, 10 chromosomes of the initial population, they had a 10 chromosome value. So, if I take what is known as an average of them, then I will get the average fitness. I will get the average fitness value. So, this average fitness value is going to help us in subsequent evaluation, right. So, that is how we say that how fit is this particular generation. Now, after that we do a selection process. So, you see there are different kinds of selection. One such selection is the roulette wheel selection. So, there is a sampling mechanism, select chromosomes from the sampling space, and roulette wheel selection is I will explain very soon. That determine the survival probabilities proportional to the fitness value, randomly generate numbers between 0 and 1 and select the individual. So, there could be deterministic sampling and there could be mixed sampling. So, select best individuals from the parents and offsprings with no duplication of the individuals, and sometimes we do a mixed sampling with both random and deterministic sampling can be done. So, you see a deterministic sampling example could be here which one some very high fitness values. Look here, this is a very high fitness value. So, this is a very high fitness value. then this is also very high fitness value, then this 38 is also high, and this 29. Suppose we select these 4 directly, then what is that is we can call as deterministic sampling, is all right. But supposing we give some randomization process and then I select, then that kind of process can be called as a probabilistic sampling method, right. So, there could be these deterministic versus random or probabilistic sampling. Sometimes we can have a mixed sampling also, which is a mix of the two, right. So, take this example of a sampling mechanism. So, select chromosome from sampling space, stochastic sampling, roulette wheel selection, determine survival probability proportional to the fitness value, and already explained. So, here what we do essentially, we create the roulette wheel in this manner, is all right. So, we can take this as the zone of kth individual, f k is the fitness value. So, this is like f k. So, supposing this is f 1, f 2, f 3, f 4. So, these are the fitness values. So, this is the kth one, which is f 5 by the way, then f 6 and f 7. So, supposing I have 7 strings, in our case we have 10. So, we do that, and then by creating these kind of what you call circle, then when we rotate this, as we rotate, what we get is the result. That result would supposing the chances of the f 1 getting selected will be, or chances of f k getting selected can be given as f k by sum over j equal to 1 to pop size f j. So, sum of all the fitnesses and f k by that. So, that will be the probability of these f kth portion getting selected, is all right. That is the roulette wheel selection, is all right. So, suppose this particular chromosome comes up, so we select it. Supposing next time the f 1 comes, then the first chromosome will be selected, is all right. So, basically selecting for what? Selecting for recombination. What are some recombinations? The crossover and the mutation, is all right. So, there are crossover and there are mutations. So, these are different kind of these things, examples. So, right. So, having known this, that how to do selections, now we know that there are different types of different types of selection. For example, we have the roulette wheel selection without scaling, roulette wheel selection with scaling, stochastic tournament selection with a tournament size of 2, then remainder stochastic sampling without replacement, remainder stochastic sampling with replacement, and elitism. So, you see, to give a basic idea that what is a scaling method, the scaling essentially is that supposing I have some numbers, right. So, the numbers are such that they are say just let us give example of the fitness values. Supposing the fitness values are 1, 2, 3, 7 and 100. So, if these are my fitness values, and then if I do a roulette wheel selection, you will find the chances of these one getting selected will be very, very high. Is it all right? Whereas, if I try to scale this, say I want to scale it by simply adding 20 to each of them. So, what will be the new fitness values? They will be 21, 22, 23, 27 and 120. So, this is the process of scaling. So, what is the scaling I have used? Plus 20. So, you see the chance of these getting selected was 100 by the 107, 10, 12, 13, 100 by 113, and here chance of these getting selected is 120 plus 113 and another 100. So, 213, is it all right? So, if you add them 3, 6, 3, 13, 1, 3, 5, 7, 9, 21. So, you see 100 by 113 is very near to 1, whereas 120 by 213 is not so much near to 1. So, what has happened? The chance of these getting selected has reduced with scaling. In other words, the population diversity has gone up. Why we need a higher population diversity? See, we have a solution space. Suppose this is my solution space. Now, there could be local and there could be global optimas. Now, suppose this is my global optima and these are my local optima. So, if I have high population diversity, then I have representations of points all over the solution space. Otherwise, if a particular chromosome is selected all the time, I have what is known as more chance of the solution getting locally focused, right, with a narrow focus, and chances of the local solution to be resulted. So, that is why it is important that we should have a balance between selection pressure, which is fetal chromosome should be selected, versus population diversity, which means the chromosome should be selected from all over the solution space, right. So, I stop here and we shall continue this in our next lecture also. So, thank you very much.